Okay, had to resume my screen recording. So there's a variety of additional complexity and additional materials you can put into the extrusions. Okay, so that's a little bit of an introduction on extrusions themselves. Now we're going to cover secondary operations. So up to this point, what we have is some version of a pipe, if you will, right? We have an extrusion maybe with a very complex cross-section, very simple cross-section, and it's just some length. And so there is a variety of things that can happen during the manufacturing process before it gets to assembly that will both drive costs, but make a better product. And so that's what we're going to cover now. An important thing to note is often the axial location of these operations needs to be extremely precise and accurate, meaning if I have an extrusion, it needs to be very precise with relation to, let's say, the distal end here, which again is the furthest end away from the patient. This is proximal because of an interface component. So say I need to access it right here, and I have some component, let's use a balloon, for example. This needs to be very precise. And so actually this would correspond to there, as well as radial position as well. So a common term is skiving. So what is it? It's removing a portion of the wall to expose an inner lumen or create a thinner section. So there are a variety of manufacturing processes, some being laser cutting, manual cutting, or chemical dissolution that's used. And so, just to illustrate this point, this is a single lumen. To access this would be very simple. You could either do it through the end or you could skive here. But say if I just had a double lumen, so this is a cross section, 1, 2. Oops, gonna be a lot of them. A lot of tubes here. There we go. So this filled in part is where the material is. To access it, I can actually skive on the side of it. And now I'm going to have access to the first lumen, and then say I can access the secondary lumen some other way. So this is what skiving is. Reflow we've covered a bit. However, I want to cover more in detail what equipment is used. So what is it? It's using heat to change the shape of the catheter, often used to join components or create geometry at the end of an extrusion. So this is a beam reflow machine. This is a common machine. What happens is it's blowing hot air, very similar to like a heat gun from this tool tip right here. And then there's a cooling flow coming out of here. Obviously PID control, etc., built into the device. So what you can do is you can build fixtures that bring the point of contact and basically reflow a very small point. So from the example earlier, if I'm reflowing two different durometers together of, let's say, P-backs, I'm going to put heat shrink right here, and then I'm going to be able to bring this section, just this section right here in this brass piece. And it's only going to reflow a very concentrated piece of area. Then I'll actually just be able to cut and remove the heat shrink and have a reflowed catheter. So that's one example. This same operation can be done at the very end with the glass die. If you want a curved tip, you can bring it over and you just reflow the section you want. So actually the tolerance can be quite high. Quite a common process. Another common process that can be used as a secondary operation are marker bands. So what is it? Visual or radio-opaque markers that allow the user to understand the position of the catheter with respect to the anatomy. The manufacturing process here is pad printing, and so you can see them here. Especially with radiopaque, something to note is that sometimes you have to do multiple layers of pad printing. You might ask, what is radiopaque? This is a coating that can be seen under fluoroscopic imagery. So again, it just depends. If it's inside of the body, you need radiopaque. If it's outside of the body, you just need a visual marker with respect to something else, very similar to like a ruler or calipers for measurement. So as mentioned earlier, this is a version of skiving, right? So using laser ablation or using a high-powered laser, you're able to get very precise holes along the length of a catheter. Something nice is you can also do layer removal. So if you need to interface with another component, here they're removing a portion of the OD and bringing it down. Drilling as well. So depending on the durometer or what you're trying to do, this is done as well. So this is basically rotary drilling. They fix the extrusion here, and then they're able to rotate it and drill very precisely. So this is very nice if heat's a problem, depending on your material. Often with laser ablation, you're going to deal with flash, which is where you essentially have material and this hole doesn't look as clean. And so if you come here and you use micro drilling, you're able to get very precise holes with no thermal problems, if you will. The temperature during the operation stays a lot lower. So besides reflowing the tip, you can also do tip forming with lasers. So this is an example where it's similar to the operation above. They're going to fixture, rotate, and be able to cut the tip to geometry you want. So that's an overview of how catheters are made, some of the driving forces and functional requirements. So now let's abstract to definitive design guidelines that will help in making catheters. So first, starting with material selection, biocompatibility is a big one because of the applications. You want to consider durability and you want to maximize for your application versus overall, otherwise your costs will be too high. The surface properties you need and interface connections. So this is reflow, this is gluability or adhesion, and then this is also secondary operations like skiving. So to abstract the mechanical properties, you want to play this game of ductility versus stiffness for your application. If, for example, if you're pushing something, you probably are going to be slightly higher on the stiffness scale. However, if you have a long-term catheter that needs to stay in the body, after insertion, you really want a lot of ductility and flexibility. And that's the trade-off you need to play with. Tensile and compressive strength, again, based on application, and kink resistance, both in theory, but I've found in practice is going to be one of the key variables to look at. And then design variables to help you compensate for everything. Cross-section design, this is going to be a large cost factor. Tolerance design, markers, and secondary operations. So this should allow for a selection of design guidelines. Now, it's not a one-size-fits-all, it's very application-specific, and due to the nature of medical devices, there's a lot of complexity involved, and hence I will not dictate that you have to go exactly one way, but hopefully there's a good introduction of, for something like cross-section design, what is available. Some good resources are websites like Zeus, and Spectrum Plastics. Really great websites and great suppliers to work with, especially for high quantity. Okay, lastly, I want to consider direct cost factors. There's no clean cost model to consider for extrusions. However, there are things that drive the cost significantly. And this is seen both in theory, but really from industry as well. So the big ones I want to call out are cross-section geometric complexity, working with the supplier to understand what's possible for your application, sticking to circular inner and outer lumens really is going to help. And then the second thing is secondary operations and their tolerance. Those two are going to be the huge cost drivers along with minimum order quantity, but to just step through this one by one. So obviously material, but usually is going to be more application than cost-based when you decide. Tolerance, same thing. Again, I covered cross-section geometric complexity. Reinforcement layers, it's good to avoid these if you don't need them. Secondary operations, minimum order quantity, and tooling. So as mentioned, it's a similar model to injection molding. And so, again, just based on my experience, I would say if you're looking around batch sizes of 200, As of 2025, this is going to take you anywhere from 6 to 18 weeks, and you're going to be looking around 20K. And so as you go up in price, or sorry, as you go up in quantity, this number is going to come down. However, this number is going to come down. However, this lead time just balloons. So when you start looking at high volume, this is moving to like a year. So really good to work with suppliers to get accurate costing. Okay, and lastly, here's a list of references from where I got my images from. So I hope this provided a good introduction for extrusions. I would really say if a concrete reference is needed, just to scroll to the top one more time. This is really the book I would recommend. And just working with suppliers for costing and relying on their expertise for what is possible with the current technology. Okay, thanks everyone.